All right, hi everybody. Good morning. So today we're going to go through this example question. Cannonball is launched at 50 meters per second, 20 degrees above the horizontal. What is the max height? How far does it go? Okay. So I kind of already had this one pre-set up prior to starting the video, so I recommend pausing, going to write this stuff down. And then here's just a really basic picture of the situation. Okay, cannonball launch 50 and then 20 degrees above the horizontal. I think yesterday I drew the angle from the launch to the ground. I do apologize that it should just be kind of like a little mini angle from where the launch is actually at. Okay? So, overall goal, figure out delta x, and I'll just say it goes like this, boom, boom, boom. We got to figure out delta y. Okay? So, kind of go with horizontal projectile motion. Let's start by kind of listing out our information that we have. X-axis wise, automatically acceleration is equal to 0. Y-axis wise, automatically acceleration is equal to the negative 9.8 meters per second squared. Okay? So, we don't explicitly know the v initial x, v initial y, but we can solve for those two things using this, okay, 50 meters per second, 20 degrees. Because remember, anytime you're given a magnitude followed by an angle, that creates a right triangle, okay? So, hypotenuse 50, angle 20, v initial x, v initial y. So now we just got to use our SOHCAHTOA. Okay. I'm going to kind of skip some steps and basically end up with this. V initial x is equal to 50 cosine of 20. V initial y is equal to 50 sine of 20. And if you want some help with that, I can help you out individually, just kind of saving some time for myself. So 50 cosine 20 equals 46.98 meters per second, and running back with sine. The initial y is okay. So a majority of the velocity is going horizontal. Okay, so what this basically saying is this: as this cannonball goes, it's one of those throws where it's not going to go very high relatively. It's more kind of go a straighter path. Okay, angle is really low. Angle is really close to 0 degrees. Okay, so it's kind of like, think back to your triangle days. As you go from 0 to 45, the displacement in the x-axis begins to shrink. Okay, and go more, or sorry, displacement in the y-axis begins to shrink. Oh man, I think I messed that up. We'll just ignore anything I just said. Ignore all that. My apologies. I truly don't have coffee. Second. Okay, so we have this bit of information. Okay, and now we have to kind of think about what I went through yesterday with our two parts, particularly for the y-axis, okay? So if we think about the y-axis from launch to the highest point, okay? So I'm going to say y-axis, launch to m, okay? Launch to maximum height. With that, I'm going to add that the v final y is equal to 0. Now, you don't have to do it that way. If you feel comfortable enough to put v final y as 0 as part of just this general y-axis stuff, you're good to go. Now, the reason why I want to do that is I can solve for the maximum height, okay? Because that's one of the things I need to solve for. Because I have the kinematic equation v final y equals v initial y squared plus 2a delta y. So I have this equation right there that allows me to solve for this, okay? And the reason why I like to use this equation, that gets canceled out. And then anytime I can zero something out, life is good. 17.1 squared plus 2. Okay, so we have this, so squaring that, so I have negative 292.44 is equal to negative 19.6. And you get a delta y, and you get a delta y is equal to 14.92 meters. Okay, so that part's done. Now let's come to the x-axis part. X-axis part, okay, remember we just have our one equation, delta x equals v initial xt, okay? I know my v initial x, I don't know time, it's a question mark still, and that's what I need to solve for. So I actually kind of need to stick with the y-axis for a little bit longer, and now solve for my time, okay? Remember, because we're looking at these in halves, okay, I can find the time it takes from launch to the highest point using this information. In fact, I don't have to use this delta y value. I can use the first equation, v final y equals v initial y plus at. Okay, so 17.1 plus negative 9.8 t. So taking 17.1 divided by 9.8. And remember, this t is 1.74 seconds. But remember, this is my t 1/2. So this is the half flight time. Time it takes to go from launch to the highest point. And I truly want the total flight time. So I'm going to take this number times 2. And my t tot is equal to 3.49 seconds. So I now have my total time. I can now use this equation, so I can go delta x is equal to 46.98 times 3.49. And we're looking for a distance of roughly 163.95 meters. Okay? So yeah, now we got a bit more work on our hands to solve these questions out. Okay? Especially when it comes to this how far business because of all this stuff. Now, usually, like you think about math classes. In math class, if you learn a new thing, like a new way to solve something, the first time you learn it's usually like the long way. You have to take all these arduous steps and all that kind of stuff, and then you take the assessment at the end, and then once the assessment's done, the teacher's like, oh, hey, by the way, here's the shorthand way to skip all those long, arduous steps you just did for the last month. Well, that actually same approach can either be taken for projectile problems. I'm just not going to have you wait. Okay? This part, this is really, really, really important that we don't mess this up. Okay? If an object is launched and lands at the same height. Okay? So if an object is launched and lands at the same height. So in this case, we're basically, I understand this is not at ground level. I get that. But more often than not, unless I specify differently, and we'll do questions like that later, more often than not, when an object is launched in this class, we're going to say it's launched from quote-unquote ground level. So unless I specify explicitly that this object is launched from anything different, it's a good assumption to assume that it's always launched from ground level. Okay, so in this case, we're saying that this cannon is launched and it lands at the same level. Okay, or same height. Okay, so an object is launched and lands at the same height. We can use the following to solve for the quote-unquote how far. Okay? So, if an object is launched and lands at the same height, we can use the following to solve for the quote-unquote how far. That's like your delta x. Okay? Just slightly different. Okay? So, the equation's like this. Capital R is equal to v squared sine 2 theta over g. I'll zoom in a little bit. Okay? R is equal to v squared sine 2 theta over g. Okay, so R is called your range. Think of that as your delta x. V is your launch velocity. Theta, launch angle, and G is a positive 9.8 meters per second. Because remember, acceleration due to gravity is negative, but regular G is positive. So if I run this same exact question, okay, 50 meters per second, angle of 20 degrees, and I want to figure out my how far, okay, using this information, I can say R is equal to 50 squared sine of 2 times 20 over 9.8. Okay, 2 times 20, sine all that. So, run it in my calculator, throw it up here so you can see. Okay, so sine of 40, 2 times 20 is 40, times 50 squared divided by 9.8. Hey, look at that, 163.97, and up here I said 163.95. Oh, buddy, that is what you call a layup slam dunk. Nailed it. I'll go 9.8 because it's 9.76. Okay, so oopsies. Once again, this equation will be very, very handy if I ever give you a question where I ask how far did something travel, but it has to be launched and land at the same height or the same level. So if I launch something off a cliff, can't use it. If I launch something and it lands on a ledge, probably can't use it because that ledge is going to be most likely higher up, okay, and all that kind of stuff. It's a very niche equation, but this thing saves a lot of time. Okay? All right, that's all I got for today. Deuces.